It's a pleasure to welcome Russ Tedrake for today's seminar. Russ is an associate professor at MIT, affiliated with departments of electrical engineering and computer science, aeroastro, mechanical engineering, as well as with computer science and AI lab at MIT. His work on control theory, locomotion, and perception certainly reflects this wide reach across departmental boundaries and disciplines, while always setting the bar high for technical rigor and robustness guarantees. Russ is also the Vice President of Robotics Research at the TRI, the Toyota Research Institute. And among his many other accomplishments, he was also a leader for Team MIT's entry in the DARPA Robotics Challenge a few years ago. I personally got to know Russ and his work by reading his beautiful paper on LQR trees from RSS 2009. As well as through his graduate course on undergraduate robotics, which I've essentially recommended to everyone who cared to listen. He probably doesn't remember this, but I also remember a lab tour that he organized during RSS 2017 at MIT, where essentially he stood on top of a desk and started explaining the vision for his lab with clarity and passion. And it was one of the few times that I had seen such a energetic lab tour. Russ has received many accolades and awards for his research, including the NSF Career Award, the DARPA Young Faculty Award in Mathematics, the Best Paper Award at RSS, Microsoft Research New Faculty Fellowship, as well as a number of teaching awards. So please welcome, please help join me in welcoming Russ and giving him a warm hello.
That was super nice. Thank you very, very much. Just to say it one more time, if anybody wants to see the videos live in their browser, you can click on the link that is that I put around with the slides.com. That's going to just advance along with my slides and let you see the videos properly. Okay, so thank you for inviting me. I wanted to talk about manipulation. I've changed my focus mostly to manipulation, but I've always liked dynamics and control and feedback control. And actually that started, Florian said something about the DARPA Robotics Challenge. You know, that didn't start at the DARPA Robotics Challenge, but that was a defining thing for me. So I, just to, you know, give you a taste of the kind of feedback control that we kind of want. This was the DARPA Robotics Challenge. We had to have our 400-pound humanoid robot drive a car and open doors and turn valves and you know, pick up screwdrivers, all kinds of crazy stuff. But actually the walking around and not falling down was a significant part of the challenge. And the reason that that worked when it worked and when it didn't work was based on feedback control. And you know, the feedback controllers that we were able to design for that were, to me, very impressive. They, you know, the complexity of that system was extremely high. We did model-based, physics-based control. You know, we didn't model Andres jumping on the back of the car, but we just asked for robustness. And this thing, you know, piloted that 400-pound robot incredibly well, right? So I want that for manipulation. I want that badly for manipulation, but we don't have those same kind of results happening in manipulation yet. And I thought I'd try to tell a little bit of that story today. Just to be clear, when I talk about feedback control for manipulation, I don't mean feedback of the arm. The state space of this problem is the state of the robot, but also the state of the environment. So really, the under-actuated part is the degrees of freedom of the object. So, you know, it's a different problem. It's still hard. Controlling a robot arm, easy. Controlling the state of the world, hard. And I don't want to just move red blocks around. I want to, you know, do things like humans do that are beautiful and complex and really break everything I know about model-based control, right? So this is one of a million examples I could have picked, but if you watch what you do with your hands, it's just really, really good. You might, though, reasonably question, I've questioned it a lot myself, of how important feedback is really to manipulation. Even in tying your shoes, are you really closing a feedback loop on your sensor observations at high rate in order to tie your shoelaces, or is that kind of more open loop? And I do think having good plans and open loop stability is a viable, interesting alternative, right? And we've seen that in a big way in robotic manipulation, where people have built under-actuated hands, these custom end effectors that can do lots and lots of interesting things, lots and lots of useful things, just by virtue of having enveloping grasps basically mastered with a passive mechanism. Okay, but this doesn't solve the whole problem. It'd be hard to tie your shoelaces with that. It'd be hard to button your shirt with that, right? It's good for niche problem, or a pretty big class of problems, but not for the generality of human manipulation. And if you look, if you like really observe yourself, and it's hard to do, all the subtle little things that you do while you're just walking around the convenience store or the kitchen or whatever, there's all the little signs, the telltale signs of feedback control. Like here's a good example right here when she's setting down the gum. You know, there's just a little bump, clearly a sensory response, and then she lands the place. And we're missing that. That simple little thing is not being done well by robotic manipulation systems today. And there's lots of good examples, but if you really watch what you're doing with your hands, I mean, it's just so good. Like all the little things that are happening below our level of consciousness. You might say, okay, I agree that's useful, but it's already solved. We've seen, you know, the OpenAI hand turning a cube. And I actually think that's an awesome, awesome project, and it's a nice existence proof, but it's still a pretty hard recipe if you want to follow that recipe, right? So making that simulator was no simple task. We'll talk more about this through the talk, but even writing a cost function for some of the complicated manipulation things we're talking about is no easy task. And although we've seen incredible success, the efficiency is rough and when in deep policy gradient, and I think our rigorous understanding of when it works and when it doesn't work is still needs to be developed. So, you know, the model-based control is just kind of at a different level of maturity. It's been around longer, and you know, the idea that we could write a balancing controller for Atlas, which was our first 400-pound Boston Dynamics robot, and then NASA asked us to do some work on their humanoid robot. They sent us this different humanoid robot, and in about 3 hours of just changing the variable names in the code or something, we got this robot up and running using the same controller. So the transfer from one 400-pound humanoid to a slightly lighter humanoid here was sort of that's kind of one of the hallmarks of model-based control when you get it right. There's other examples that we've done through the years that have impressed on me the power of more mature control. You know, we have airplanes that can land on a perch a number of years ago now. But the thing that was most compelling for me about that project was not only that in, you know, a couple seconds of computation could we design the controller, but a minute of computation you could come up with certificates of when that controller was going to work. We knew, you know, when the wind was too strong and things like this. There were just, it's a level of sophistication and feedback that we don't get from policy gradient yet. Okay, so there are a lot of technical hurdles to solve if we want feedback control for manipulation. I like to think about a lot of them, but I can't talk about all of them. So I tried to make a quick list and pick a couple. So dexterity with feedback and contact. If you give me a perfect simulator with perfect state estimation, everything, I know the model, and ask me to do something like tie my shoelaces, that's still hard. I don't have good solutions for that in general. But even in simpler tasks, you know, I think we have open questions about what is the right way to design and work with tactile sensing, with how does that change the contact mechanics. I'll have a teaser about that at the end if we have time. There's really good questions about robustness, because, you know, it's one thing to be robustness to gust disturbances if you're an airplane and those gusts are drawn from a, you know, basically a whitening filter on a linear system from a Gaussian, you know, IID noise. We know how to do that. But if you ask me to build a robot that can work in your kitchen and my kitchen and everybody else's kitchen and has to work with slightly different dishes and slightly different lighting conditions, we don't know how to do that. So there's really good problems that manipulation brings to the forefront, as other areas of robotics are also. And then just to, you know, to architect the feedback into a bigger system, which we want with these manipulation systems, we need to solve some of the really fundamental problems. But I have to pick, so today I was going to talk about some of the challenges of even doing feedback control when you've got a camera as your primary sensor. That's already super hard. It breaks a lot of the things we know how to do. And that begs the question of state representations. I'm looking at Tim on my screen here, and I'm thinking of, and Jonathan, I know people are thinking about, state estimation and representations and the like. And so I thought I'd talk about that a bit today. Okay, so just to be super clear, this is actually it's a full 3D open, a 3JS simulation running in your browser right now. You can actually zoom in and out. It's all interactive with you. It's not impressive demo, but it's just the first of those kind of things. But just to be super clear, the state representation problem I'm talking about now, I know the joint angles of the robot, and I'm actually fine with that as the representation of positions and velocities of the robot. That's fine. How do you represent the state of the block? Okay, well, the natural choice is I've got an SE3 pose plus some spatial velocity. I'm not talking about which representation of SE3. Are we using quaternions? Are we using, the Jonathan's recent work on the SE3 representations? Are we using it? I'm not talking about that. I'm talking about, how do we do state representation for this, right? So yes, there is a state of the system if I wanted to write a simulator, and each of those pieces of the onion have a pose, and they have geometry, and they have dynamics, but I don't want to think about that. Like if my first step of the algorithm is to estimate the state of the onion, and the state space is changing like this every time, then somehow we're dead in the water. So I mean something different when I'm saying state representations. I'm saying, how do you write the state of an onion while you're chopping it? Okay, that's a different question. And it's a hard question. We'll get to it a little bit by the end, but let me start with a smaller step and try to work from our inclination of SE3 pose to something just one step maybe more, trying to go towards this state representation question. And there's a sort of useful sweet spot we found in the group about thinking about how do you manipulate a category of objects. So what do I mean by that? So I don't want to just manipulate a mug. I want to write a manipulation controller that can manipulate any mug, right? And so in this video, none of these mugs had ever been seen before, but we can still do not only pick and drop kind of tasks, but actually a precision placement of that object, despite having broad uncertainty, relatively broad, category level uncertainty in the geometry. So let me start by talking about key points as a stepping stone for state representation. So we did a couple different tasks in that paper. We did mugs, we picked up shoes and put them on the rack. And again, it's not just pick up the shoe by whatever the geometry says and drop it off, but it has to align the shoe, the toe has to be in the front. It has to have some semantic understanding of what the shoe is, some bigger idea of objects than just pick and drop would do. So how do you do that for a category of objects? So we want to manipulate potentially unknown. We'll stick with rigid for the formulation first. Objects from a category into desired target configurations. And the temptation is to write a front-end system that estimates pose. And already with the category level question, we found that wanting, right? It's falling short. So it's hard to define a canonical pose that's going to work for all the tasks you care about, for a sneaker, a high-heeled shoe, a boot, and everything across a category. It turns out it's very hard to just pick a canonical coordinate system that you can identify robustly. And if you get rid of that, then how do you even specify the task? What's the cost function? Some people would say, just show me an image of the mugs on the rack, right? But if you've got a dish loading robot and it's looking at a dirty sink and you just give it a picture of a clean sink, that's a pretty underspecified problem. Who knows what's gonna happen, right? So it's hard to think of images being the only way to specify tasks. So key points are this great thing from computer vision. Started with open pose, but it's lots and lots of good work in key point detection, and they happen to snap right in to all the classical things we've been doing with kinematic planning for robots. So imagine just dispensing with the 3D pose, and just think about labeling a handful of key points for your object, and then writing costs and constraints directly on those key points, okay? Because these systems work, the perception front end works well in practice, we found these to be much more robust than trying to build a pose estimation network. It's just the key point networks are just easier to train, more robust. And it turns out you don't need much more for a lot of tasks. So it plugs right into our pipelines. We had already been thinking about, inverse kinematics, kinematic trajectory planning with a relatively rich library of constraints. You could say, for instance, I want the hand to be in a certain place, or you could underspecify it. You say, I don't care where the hand is exactly, but I'd like the palm to be, parallel to the table or something like this. And these manifold type constraints, which there are many in walking, are the kind of thing you can do directly with key points. So I have to say, though, the key points are not a sufficient representation by themselves to do the task. They help us say like what the transformation of the object I'm looking at should be in the final solution. We just say, I'd like the key points that are currently here to be in some different transformation. But in order to actually pick it up, you need to have somehow a more complete geometric understanding to just do the grasp. It turns out a lot of times that just even your one-off point cloud is enough to do a grasp. The simplest grasping algorithms actually work pretty well, and you could put any grasping algorithm in here. Doing a little bit of dense reconstruction goes a long way, and I'll show you some shape completion. But all of these are kind of simple, real different additions after just the idea of specifying the task with key points. So just to say, we kind of hammered on this, and you could walk in, if it was pre-March, you could walk into the lab and take your shoe off and put it on the table, and very likely it would put it on the rack in the right orientation. And if it didn't, then we would ask to scan your shoe and then come back tomorrow, and it would be good. This was a simple but robust pipeline. And like I said, you can combine it with shape completion to try to do, if your immediate views are occluded and you want to pick something up and have some understanding of its extent, so you don't collide between the mug and obstacles, for instance, things like shape completion networks work well there. Okay, so that notion of key point is starting our discussion of state, but it's let's see what it does and doesn't do, right? So first of all, they are geometric. They're attached in some sense to every instance. They're attached to the geometry, so we can transform them in affine ways, for instance. They're also semantic. Some human came and said, this is the nose of the shoe, this is the tongue of the shoe, this is the heel of the shoe, and so that allows us to write semantic sort of specifications of the task. But they required human labels, and that's no good. So if we forgo semantics, can we forgo with humans and self-supervised, right? Okay, so the next sort of core technology is using these dense correspondences, and this is work that started with Tanner Schmidt and Dieter Fox and Richard Newcomb, and Pete and Lucas maybe brought it to manipulation and showed that it's actually surprisingly good representation for thinking about objects that you want to manipulate. And so I'm going to show you videos like this for a little bit, and so I want to make sure it's clear. So on the left is a picture, one frame, and then there's a mouse that's hovering over one point of the hat. On the center and on the right are just a live stream of a different video, okay? And it's trying to show you the point in the next videos are the point it believes corresponds as closely as possible to the point on the left. So if it's doing a good job, you think, oh yeah, it found the same place of the hat despite having a very different view of the hat. That's success. The one in the middle shows the heat map, which is its kind of uncertainty about where those points are. So maybe I'll even, now that I've explained it, I'll let that run one more time. So you can watch that it's tracking, its corresponding points in the new video with the the target point on the hat. The way we do that is it's a self-supervised pipeline. We basically scan the whatever object, we throw an object on the table, we roughly scan it with the wrist-mounted RGBD and do a dense 3D reconstruction. And then we back label everything, every one of those images. Now we can say, in those two images from different views, this was the same point on the geometry. So that allows us to go back through and label the pixel-wise loss, saying these two, in these different images, this pixel's the same, these pixels are different. And you just make a cost function like this, and you can get reams of data very quickly. If anybody has followed the early work on this, we've gotten better at training the correspondence networks. So, just the one on the top is sort of what it looked like when we originally published the paper, but now we're getting much sharper correspondences with the slightly updated training procedure. Here's the crazy thing about the dense correspondences is if you train them on a bunch of different hats individually, and then put down all those hats or different hats that had never been seen before in the view, it seems to have learned to correspond across instances, across the category. It uses a consistent representation, maybe something about capacity or whatever, but we're able to do either, if we put multiple hats at the same time, that it'll learn to distinguish between them. If we train each hat at one at a time, it learns this common representation, and we can correspond across hats. So this gives us, and it's a little unsettling that we don't understand exactly why that's happening, and we've got an ongoing project to understand that better, but we've been exploiting it heavily, is to say that we can now do correspondences across a category of objects. So dense descriptors, these dense correspondences give us a way to do these self-supervised representations, which I'll show you, can use as self-supervised key points. And if that's all we had, if we just had correspondences alone, there are some tasks you can specify. So at the original dense object nets paper, it was like, go pick the object up from its tail. It's a caterpillar from its tail, and it'll just always, you can put it down in a new orientation, a new caterpillar, whatever, it'll pick it up from its tail. But that's a kind of boring task, but it shows that there's some utility in that representation. But we wanted to see how more, if we could do more interesting tasks and more dynamic tasks. So on to imitation learning. So a lot of people are thinking about visuomotor feedback policies, right? Cameras, pixels to torques, if you will. Sergey and Chelsea were leaders in this area. If you look at a lot of the architectures of a lot of those systems, I was a little surprised when we started looking more carefully. They are relatively huge networks, but they're relatively huge perception networks with relatively small policy networks right next to them. So there's some big, possibly often pre-trained network here that is then being shoved down into a relatively low dimensional latent space. And then the policy itself brings in the state of the robot, for instance, and is a relatively small couple-layer, multi-layer perceptron, okay, to do actions. So the question we wanted to ask is, what if we take off the original, perception network and put our dense descriptor network in the front end? Now the dense descriptors by default give a whole image of descriptors. So they give the whole descriptor space, these images that look like this. So we wanted to get down to a small network for a small policy. So we basically downsample. We pick a handful of points to represent our key points, a sparser representation of the current scene, and put them through our standard dense descriptors correspondence function. And then we still use our little itty bitty feedback policy at the end. Okay, so there's a fundamental problem if you're using these weirder state representations, the more implicit state representations, of how you even specify the task, right? And we gave away the semantics, so we don't have a good way to specify the task except through demonstrations. So that's why we started with imitation learning. Was, first of all, we could take controllers that we liked in simulation, or we could take Pete, who I like, in doing training, doing teleop in reality, and can we ask the network to do the same thing with visual feedback? And the simulator was actually super useful in just debugging and understanding, choosing architectures and everything like that. It turns out a relatively small policy, with LSTM, about 100 LSTMs could do these relatively simple tasks. And once we got that all figured out, we retrained from scratch on a new set of examples in reality. And this was the first time where, for me, it was like, wow, we got robustness back in our manipulation system. The kind of robustness we felt like when we were pushing on Atlas, our 400-pound humanoid or whatever, we started to see this in manipulation. We were doing non-trivial tasks, deformable hats, flipping shoes up. The shoes, it's like beautiful to us and weird to everybody else. But if you think about the dynamics of flipping up a shoe, and every shoe is very different, that's actually a pretty hard task. And I'll show you some more of the plates. But it's a very robust system. So again, the key is this, that while it's executing this, it's using these dense correspondences. And the takeaways from Pete and Lucas was that they saw very good performance, very robust performance, but as expected, it was sort of, their intuition was it's sort of the system would work if you stayed near your imitations, and it would do whatever arbitrary things when you're outside. And they had this heuristic idea that if there's the convex hull of your training data, of your imitation data, sort of defined it. And in a few very simple low dimensional projections, they kind of told that story. But that, that thought process has served them well. Okay, so let's dig in on one of my favorite examples of that. So this is just picking up a plate, but it's got some pushing in it. That's actually an unstable pushing. The plate wants to sort of weather vane around and get behind you. But so that's a non-trivial multi-contact task, and it's closing a feedback loop with the camera, right? And despite having the camera and the RGB values just changed a bunch, those dense descriptors give us this robust representation that can ignore the irrelevant details. The policy seems to do very well despite distractors and differences in the dynamics. This was the first time where I was like, you know what, we're starting to see robustness again. That actually is not an arbitrary example. I've been thinking about loading dishes for a while now. At Toyota, we've got an example system that we're trying to bring to like the 5 nines of maturity in terms of doing the dishes and thinking about the interesting questions about robustness and distributional robustness, lifelong learning, these kind of problems. But one of the most subtle things it does, let me just play it again, is that when it has to pick up plates in the sink, it's actually a pretty sophisticated process. And the controller that you see running in this video, that's running day in and day out on the robots at TRI, is actually written by C1. It's a human engineered controller, and it's like 6 lines or something like this. It's very, very simple. It's, and time again, I've seen clever people like C1, we like to call them robot whisperers, who can write very simple feedback controllers. They often have the state machine kind of feel where they go until you touch, and the robustness of this is impressive. It has a lot of things in C1's head about of decisions he made. And we're starting to see similar robustness, but not similar simplicity from the deep approach. We're banging on this problem with everything we've got. We've kind of reduced it down to a planar version. We can even reduce it more to a point finger. We've got versions where it's just tractable enough that we can write it as a POM-DP, for instance, and ask what is the robust policy over when you have belief over the distribution of plates, and there's versions that go that sort of as a stepping stone from that point finger. This is an intermediate one. Where in this particular video, we were using policy search to hammer on it, but this is, it's good to have benchmark problems, and this is one that served us well, and we're hammering on it with everything we've got. Okay, so very happy with the performance, super happy with the performance of that imitation learning. Hate the fact that we have to do imitations, and if you change the task a little bit, you basically have to redo your imitations. So how do we get to the point where we're designing these things more reliably and generalizing to more objectives and tasks? So recently we've been trying to use those same representations to do model predictive control, online planning. So instead of learning just the policy directly, we're trying to learn a model of the dynamics of the key points. Okay, so unfortunately this was, the experiments in this part were deeply affected by COVID. Lucas was graduating in the middle of the summer, and he got back in lab to do a few experiments, but the hardware experiments were crippled by that. But basically now we still use our dense descriptors. We still downsample to a sparse key point representation. There's even a couple tricks in there to try to choose the right key points that are not occluded during any given task. And then what we do instead is we, instead of learning the policy, we learn the dynamics of those key points in a deep network, and then do online planning with model predictive control in order to track them. So now, instead of doing many demonstrations, we still don't have the notion of state well enough to do the specification of the task. So we now give one demonstration to say, this is what I want you to do, but using the history of previous demonstrations to train the model, we can plan on the fly and accomplish a new task. And that worked very well in our preliminary experiments of it. So I think it is possible, then we did many more experiments on older data and on simulation-based data. Our takeaways so far for this have been that we can train a network, just a feed-forward network in that case, to predict the key point dynamics, even for pretty complex tasks. The hat on the rack is deformable and everything. But the step of using it for trajectory MPC, a lot of people sweep it under the rug. They say, well, just do, someone else is thinking hard about that. But it's actually very hard, and a lot of people do cross-entropy methods, which I think that means we don't understand how to do better. So actually, Florian has some work on that, right? So I think Lucas said it nicely in his defense. He keeps wanting to do, he wants to do manipulation, but he wants to do control, and he says, but perception's always the bottleneck. Perception's always the bottleneck. And finally, at his defense, he said, you know what? Finally, in this, we're starting to feel like the key points are pretty reliable. They're sufficient for a lot of tasks, and planning and control is the bottleneck now. So that's interesting. People keep asking about this sort of tension between deep models and first principles physics models, and I'll talk a little bit more about it at the end. But this kind of put us squarely in that thought process. So what have we done so far? We wanted state representations for category level dexterous manipulation. And I've offered that key points are actually a pretty good starting point. They can represent category level geometry. I think you can combine them with local sensing and dense reconstructions to do a lot of tasks. And then actually, even for state representations of predicting forward, you can learn the key point dynamics. The task specification I tried to emphasize a few times. It's really nice when you've annotated semantic key points and you have some notion of like, this is the handle of the mug or whatever. When you give that up, then you can still do some things, but we've been using demonstrations to use the self-supervised key points. Key points are not everything. We don't claim to be. They are talking about the geometry of the task. They won't tell you when the eggs are done cooking. They won't tell you, a lot of tasks are hard to specify with key points still, but they're a useful stepping stone. Let's get back to that onion problem. So we really did think a lot about how to chop an onion. Turns out though, as much as I like to call it onions, it turns out you shouldn't use onions. Let me save you the trouble. The lab smells better and the carrots are brighter orange and they last longer. They don't get smelly as quickly. So I highly recommend using carrots instead of onions. But also there's, the video I showed was this big kitchen knife chopping an onion. We thought, let's not start with the big kitchen knife, and we'll start with manipulating the piles of onions that were already on the cutting board, because that still begs for a better state representation. So we started with that, okay? And so the specification here is to push. You've got a slider now, a dull slider that you're trying to push the carrots into some area, some target set on the board. The exact, as long as all the bits are in the target set, you've accomplished the task. And the reason we wanted to study this was about state representation, but it was also really about this question of feedback from pixels to torques. And in controls, it's often the case, you think, what's the easy version of this problem? And there's some limiting case where you can think about it as like a linear quadratic problem, or maybe some limiting case where you can think about it as a tabular problem. And we have like really good solutions and we understand everything about it. I hadn't been able to do that for pixels to torques. Anytime there's a camera in there, there's no limit where it feels like LQR, right? So we were hoping to make progress on that. So the problem statement is find a single policy from pixels to torques that is invariant to the number of caret pieces. So I don't want my representation to be, melting if I throw a few more caret pieces in there. And just going to move the caret pieces to the target set. We have discrete pushes. So like many people who do pushing with robots, we're parameterizing it from the start position, end position of the pusher, and assume that it's normal. So it's a low dimensional state input space. And then our outputs, our observations are the images, or vectorized versions of the images. So what would it mean to try images as a state representation? A lot of people say that these days. So what does that mean to me? So we have our original image. We're gonna process it down to a thresholded, grayscale, lower dimensional image representation. I'll call that I, and we'll use Y to denote the vectorized version of that. It turns out if you do think of that image as a state representation, and I don't love that word, but we'll talk about it at the end, then it's actually relatively easy to do control. The control task here is not very hard. There's a simple control Lyapunov function, for instance, is one of many things that you could do to make it work. But the intuition here is let's just assign a score given all the weight, all the pixels you see outside from above in that grayscale image. Basically, the current score the controller is getting, the Lyapunov function, cost to go, if you will, is just the accumulated distance between all the particles and the target set. So once you're inside, it's 0, and then it's the distance, Cartesian distance away. Now, it turns out if you think about that in image space, it's kind of elegant in the sense that you can just make your cost image and basically Hadamard product with the current image to evaluate your cost to go, or your Lyapunov function. In order to make the decision, though, you have to understand the consequences of your actions. That requires some sort of forward model. So we tried the deep visual foresight from Chelsea and Sergey, and it worked as promised, but the whole system together didn't work. We were able to train networks that could predict the new image with pretty high reliability, but small errors in that prediction could lead to sort of catastrophic failures in the planning. If it hallucinated carets or hoped that carets would evaporate, then it could get stuck in these infinite loops. So we were talking about all the different ways to address that. And it's like, we just need to somehow tell it not to hallucinate carets. How do you do that? And there was a conversation where we said, what's super annoying is it would be very easy to tell a linear model that if you just had a matrix representation, we could impose conservation of mass on that pretty easily. In fact, you don't even need a strict conservation of mass. You can just say that nothing gets destroyed, and you should describe your image data, and that's enough to sort of cause that regularization. So we tried it. We said, okay, what would it look like to map a current image to the next image by a linear transform? And the reason it's not crazy is because if you think about what's happening at the image level, you can think about there's a bunch of pixels. Right now I'm about to do an action, and what does that action do? It's not quite a permutation matrix, but think about it like that. It's permuting the pixels that were in the path of the pusher over to the edge wherever the pusher ended, right? So it's taking a bunch of pixels and it's just changing where they are in the matrix, and that's a linear operation. Because things are grayscale, it's a little bit more than that, but it's not crazy to think about it as a linear operation. And it worked pretty well. So if we just sample data, for instance, we take an image like this, we do a push through that image. This is what the data looks like coming out. The linear map can predict this, and the deep visual foresight map would predict something like this. I mean, looks a little better, but the linear model's pretty darn good. It just kind of breaks what you'd think what a linear model could do maybe, but it's good. The cool thing is the linear model is easy to introspect because each row of that A matrix is an image, and it's like the receptive field of the pixel at a certain location in the image. So you can go through, and if I show, like in the middle here, this is the receptive field for this, okay? The receptive field for that pink is this here. So when you get here, you see that there's all the pixels that were in the path of the pusher are likely to end up at that pixel, for instance, and it gets to be an empty image if the pink was inside the path of the pusher. Okay, so here's the experiment. I showed it a little bit already, but we've got an RGB camera, a real sense, and we've got our pusher here, white cutting board, bright orange carrots, and off it goes. So this turned out to be quite robust policy. It didn't have the problem of hallucinating or evaporating carrots. It was trained with, actually less data and to get a better fit. To try to follow up on Lucas and Pete, we started disturbing the carrots, showing the robustness. Okay, so let me just be super clear. I am not saying that linear models are better than deep models. This will not work for most problems. What I'm trying to say is that there is an interesting sort of corner case in the space of visual feedback problems where pixels to torque actually does get sort of easy again. Okay, and what is that corner case? The right way to think about it, I think, is when each pixel moves effectively independently. That's the assumption that we're making by putting linearity on here. And if it's helpful for you, I like to think of it as the image is I have like a probability density over my image, and the linear map is the transition matrix. And so the probability of being in any one pixel of the image can move under the transition probability, and all the tools of Markov decision processes become available to you. Okay, so we talked about, I brushed over a bunch of things. We talked about state representations and feedback from pixels. Let me just wrap up here. I said a little bit about deep versus physics. I showed the big punching bag gloves or whatever. This is a conversation often these days, and I feel like it's a little bit off. So we have systems. We try to model them with models. We could choose a state space model. We could choose an autoregressive model. There are different ways to write models. And I think it's true that our Lagrangian mechanics physics-based models tend to take a state space form. And that's good, that's compact, it can be minimal, in many cases, right? Recurrent networks fall under that form too. They're doing sort of internal state models. But when we're talking about these image-to-image networks or history of images to networks, I don't like to think about that as a state. I think about that as an ARX or RMAX model, okay? And I think that's maybe the better way to think about it. Of course, you can go back and forth, and that's what people are doing in the language. Is you can take your history of any finite history of inputs or observations, you can call that your state. Okay, but for onions, laundry, peanut butter, okay, I don't think that our physics-based models are somehow failing due to the representational power. They're very rich. I think what they're failing on is these unreasonable burden of trying to estimate the Lagrangian state in the parameters, right? The state space models are beautiful and compact, but they put the burden of state estimation on you. And what we're seeing in the input-output models is you don't have that burden of state estimation, so they seem to work well and they seem to work better. But I hope that, I think those models, the deep models, they can be predictive or not. That's a separate question, but they are hard because we don't have as good tools for planning, control, design, and analysis when they get really complicated. Okay, so I'm hoping that we can rectify all of this and get, if input output is the right way to do it, or state representations that are reasonable to estimate, then good things could happen. But I'm a big advocate for simplicity. I don't, I think to some extent if we don't have simpler models, it's going to be hard to do better planning and control. So I want the next, Newton or Galileo or somebody to come around, and I would ask them to work on onions and laundry and peanut butter. Okay, I've got a teaser about soft manipulation. I'll skip that for now, but if people want to see it later, I can. My manipulation class is a Zoom class all of a sudden this fall, and it's going to have these 3D interactions so right now coming to your browser is a 3D renderer that is our full simulation. You can interact with it and the like. And I've been spending my summer writing JavaScript in Google Colab so that I can bring a full manipulation stack to you over Zoom. And so it'll be online if anybody's interested in checking it out. All right, and then my obligatory ending is I have to spell MIT in the carrots. So I'll take any questions. There's the claps.
All right, maybe we can get some questions from the group chat. So Homanga Bharatwaj asks, he says, thanks for the awesome talk. Could you elaborate a bit on why you believe CM is not the right way to be doing planning using a learned model? And any intuitions on how we can do better?
I'll give you a philosophical answer first, but we'll see. So, I mean, Florian, you've got a paper, I think, on why people are using cross entropy, combining it with gradient methods and the like, right? So this is
actually, Homanga is the first author on that paper. That's why.
Oh, very good. Okay, so now I understand the question. So why I should ask you, but I think it's very weird that people are resorting to CEM for something that does have gradients. First of all, the philosophical answer is that one thing that's very different about physics-based models and deep models is that physics-based models are not universal approximators. They take a stand and they say there are some conservation laws, there are some constraints, there are some things that will never happen, right? Matter will never be created or destroyed, energy will not be created or destroyed, and that, I think those constraints give you the structure and the problem that we often leverage, whether it's control affine or positive definite manipulator equations or inverse dynamics being sparse or whatever. And it's really, decades of work finding ways to exploit that structure that has made our planning and control algorithms so powerful. So I worry, I think you could put some of that in maybe in deep representations, but if we don't say anything and we just say the model could be arbitrary and arbitrary complexity or whatever, then you're tying your hands in terms of what you can do in terms of better control. So that's why I really want to find, I think there are some models that are very simple, like the dish pickup. The controller there was extremely simple, and we're not finding those yet. So I think there's more work to do.
Great. So Philippe Nadeau asks, tactile sensors can provide very precise local information about contacts. Are current optimization algorithms able to deal with the quantity of information involved by the skin of an artificial hand?
That's what the last video, I'll play it while I answer, but we have some videos of dense geometry sensors that we've been building at TRI, which blur this, or they combine these two ideas of one is the mechanics of the interface changing, and that it's better to have surface patch contacts and compliance than to have point rigid contacts, even though they're today harder to think about. And then you can do these dense sensing and rich slip detection, rich force detection, and the like. So I don't worry about the dimensionality of the data. And you're right, it's super good. Like the problem, I'll maybe stop playing that just so people can listen. But I think the problem with head-mounted cameras is as soon as you put your hand down in front of the object and things are about to get interesting, you've occluded your head-mounted cameras. And if okay, I'll put a camera in my palm. Okay, but then the minimum range of the sensor gets to be the problem. And really, it is the case that our camera-based sensing sort of die out right at the part where the manipulation gets interesting. So tactile, I think, has a huge role to play. It's a different problem, like I say, not because of the dimensionality, but because of it's intermittent, it's it's impulsive, it's non-smooth. There are other reasons I think why it's important. We've shown that we can do pose estimation through it. We can do slip detection and a bunch of the standard things you'd like to do. Like the right state representations that merges those, we don't have yet.
Great. The next question is by John Kelly. John, do you want to ask it?
Oh, no, you can go ahead, Florian.
Okay, so John asks, to what extent should we be willing to instrument the environment or bend to the needs of the robots? Or do we just force robots to be as good as us? Or expect them to be so in the near term?
I mean, that depends if you're trying to make a startup or if you're trying to solve intelligence, I guess, right? Yeah, I think we often handicap ourselves, and we can make robots work a lot better with a little bit of instrumentation. And at some point, environments will be built for our robots, and but at the same time, there's some fascinating questions about how do you do roughly what humans do with the sensors roughly humans do. I think we've been too conservative in that way, of course. I think our fascination with dexterous hands maybe lost us a decade or two. But, you know, I do think the scientific problem is what's interesting there.
All right, Adam Hall asks, first of all, he says your talks are always awesome. And he asks, where are you headed with in terms of combining many different sensor modalities to achieve similar robust manipulation?
That is such a good question because, yeah, I mean, so we said key points are good for perception. I like to think the nice thing I like about the dense tactile sensors is you can basically think of it as a short range depth sensor in your fingertip, right? So it does fuse right in as just a multi-camera kind of fusion problem in that sense. But at the same time, there's a deeper representational question that we haven't cracked yet about it. You know, what fundamentally do you do differently if you have slip available and you have these other things? So key points I don't think of as the only solution by any means. It's just a stepping stone. But there are probably some really good representations that lie at the intersection to be found.
Cool. So Sepir Samavi asks, he thanks you for the talk, and he asks, could you comment on how to define robustness in manipulation tasks?
Mm-hmm. I mean, I think people are too quick to discount the classical definitions of robustness. I think they're still good, but it's true that category level robustness, lighting robustness, you know, the types of things that people do in domain random. But so, you know, the fact that people are doing domain randomization, like putting cheetah patterns on stuff, I think that's both awesome. Like it's because it helped us escape from this minima of like ellipsoidal uncertainty sets and polytopic uncertainty sets, and realize that there's good things to happen if you are much more aggressive with your distributions. But it also probably means, I mean, there's a lesson from robust control, right? So if you write a really broad uncertainty set and ask for your controller to do everything in that uncertainty set, then you can only do that when the problem is really easy, right? So probably if the leopard print stuff is working, then those problems are easy, and that's probably true. I think we have lots of problems that are easy, we're just starting to solve. But if you're, I don't know, the Millennium Falcon trying to do like a hairpin maneuver as the doors are closing, you can't say, okay, but the Death Star might be here or here or here, you know, that just doesn't work. So as the problems get more high performance, more at the limits of what the robot's capable of and the perception's capable of, the uncertainty distributions have to be narrower. That doesn't mean they have to be ellipsoidal or polytopic. And this notion of like the distributional robustness across different, you know, a robot that's doing a high performance task in one lighting environment or another lighting environment, or with one set of mugs versus a different set of mugs. How do you generalize across that is super interesting. But I'm optimistic you can grow the tools from robust control to that, into that, you know, level of problem.
Great. So Mansour asks, he thanks for the presentation, and he asks, can the link to your online manipulation class this fall be posted in the chat as well? We'll make sure to give you the link through our Slack channels. We'll figure that out.
Yep, it's manipulation.
Yep. Does anyone else have questions? Okay, Oliver asks, do you think there is a certain ceiling on manipulation performance based on hardware limitations? It seems there are a lot of examples of embodied intelligence where the intelligence is implicit in the design of the hardware. Yeah,
it's a really good question. I think there's kind of the two camps, well, the three camps. I think there's like the dexterous hand camp, and you know, we'd like to have something that has all the articulation and dexterity of a human hand, but then they spend a lot of time fixing their hands because those hands aren't very robust. And then there's the under-actuated hand where you can do lots of things with a jamming gripper or something. But there's, you know, like the Matt Mason camp, I guess, if you will. Somehow the camp which says, look, if I give you one of those little grippers from the toy store, I probably have one around here, but you know, you know, and I gave your brain that gripper and sent you into the living room and asked you to do something useful, it might take you 4 times as long or something, but you can do a lot of things with a really simple hand and a good brain. So there's this camp says, you know, you should be able to do a lot with a very simple. I think it's too simple to blame the hardware, but at the same time, you know, advances in hardware can cause like lightning changes in what we can do, right? I mean, when LiDAR and Connect came out, right? Just think about what that advanced. So it could be that our hardware would accelerate what we can do, and I think we should be working hard on it. But I don't think we can blame the hardware for our inadequacy and feedback control.
Mm-hmm. A couple more questions. So I guess one question that I had was about the right state estimate. So there have been many works in terms of introducing these bottlenecks for state estimation, where you have to forget as much of your observation as possible while still being able to get a representation that works well for the task. So I guess that begs the question, is the right state representation very task specific?
That's a really good point too, yes. I like the bottleneck idea. I think the machinery that the derivations we have in terms of information bottlenecks and the implications they put on policies are too weak right now. I think that they don't actually put a strong prior, if you will, on the, it basically says, you know, don't learn. If you don't have much data, don't learn, kind of is the, so super task specific. I think it has to be part of the discussion. I mean, the representation you want for the onions is very different depending on what you're trying to do. If you wanted to somehow, I don't know, make a sandcastle of onions, you might need a different representation than if you just want to make a salad, right? So hugely important.
Great. And final question, unless anyone objects. So it's from Sam Sinha. He asks, how can we measure robustness generalization on an axis? For example, in vision, you can rotate the image 30 degrees instead of 15, but how can you do that in robotics manipulation? And this sort of question has is related to sort of defining generalization for classifiers and talking about distributional robustness in classification versus talking about distributional robustness in control and RL. So how do you think about these definitions?
Yeah, that was both very specific and very big. So like when it comes to like uncertainty over distributions of pose, for instance. I mean, one of the things that happens a lot in these problems is you have some symmetries in your geometry, for instance. So like your mug, you know, it looks the same here until the handle becomes visible, and then it becomes interesting. So how do you write a distribution that is not, I mean, I like Bingham, you know, but I think there's something more going on there too, right? That is, you know, quite characteristic of these geometries. It's got the pieces of rotational symmetry, but it's not completely symmetric. You know, we've used tools to think about that, like even numerical differencing on rendered images and stuff like this, give you a sense of how you can do that. Sorry, what was the high level question again, Florian?
The high level question is, we have distributional robustness definitions for classification. And I guess the question is,
how do you get that feedback?
Yeah.
Yeah, no, I think that's really good. I don't think that formulation is far off. It just feels really hard. So the idea to say, I think we can, you know, in simulation, for instance, we can control distribution shift. We can study robustness in terms of that. I think you can write metrics down. You know, the basic idea of I've done this many tests in simulation, I've done this many tests in hardware, now I'm going to go into a new environment. How many tests does it take? Or the distributional robustness story would be like, if I take a passive scan of the new environment, can I make a prediction given just the training set, but not the test? Then can I say something about my expected performance if I'm going to deploy my dishwashing robot in a restaurant or something? Those are good formulations. I just don't have any reasonable bounds for them yet. But I think I think the formulation is good.
Great. So I think maybe we can land the plane here and say thanks to Russ once again.
Thank you all for your questions. Yeah.